Okay, let's start out by I'm going to show you how to download CVX, and then we're going to run some examples on CVX. So if you open up your web browser, and I'm just going to do a search on CVX download, and you'll see this site, CVX Research. And I will click on there, and now you'll get a download page. So depending on the operating system that you're running, you will select the appropriate download. So I'm running Windows 64-bit. I'm going to download the Windows 64-bit zip file. So I'll click on that and I'll save it. I'm just going to put it on my desktop for now. And now that is downloaded. Here it is. And now what I'm going to do, I need to find a good place to put this permanently. So I'm just going to navigate drop it in here, and I'm going to extract the zip. Okay, so I'm extracting that to my program files, x86 folder, and while that's happening, I'm going to open up MATLAB. So what we will do, and you'll see the installation instructions. I'll just bring this window over here. The installation instructions are here. Here's where I did the download, and you'll see, that the installation instructions appear down here. It's very straightforward. So we'll follow those. So what I want to do is I want to make I'm going to navigate here. So here's where my CVX is. So I'm going to make this my directory in MATLAB. Okay, so my path is C program files x86 CVX. And then once I do that, get rid of all this stuff. In my command window, I am going to type CVX setup. And it'll run through the setup. And that's pretty much it. So now I have the CVX packages available to me inside of MATLAB. Now let's look at let's just kind of look at getting started with the CVX program. We'll run through some examples. Okay, so just clearing that out. And let's run through a quick example here. These examples, I'm going to get examples from the CVX User's Guide, and then also there are examples in this examples file here that relate to examples that are in the text. So these will be very useful for you when you're doing your projects. As in fact, here you go. If you go under, let's see, if you go under examples CVX book, here you'll see chapter 4, chapter 5, 6, 7, 8, and 11 examples, specific examples from each of the chapters in the book, which will be very useful for you. We'll go through one or two of those, but first let's just do something very simple so that we can understand the syntax of how to use CVX. Now, CVX is working inside of MATLAB, so you'll see I'm going to, at some point, I'm going to begin CVX, but I can always use any MATLAB commands that I want inside or outside of the CVX program itself. So I'm going to open a script here, and we're going to solve a least squares problem. We're going to minimize the 2 norm of AX minus B. So that is norm of AX minus B, and we're going to do this just on a random matrix. We're just going to generate a random matrix here, random A matrix, random B vector, and just, I'm sure you guys are mostly familiar with MATLAB, but let's just, I'm going to run this. Okay, so now this is saved. I'm going to run it, and you'll see that what's happening is I'm generating this A matrix and this B vector. And the A matrix, you can see it has 8 columns, but it has 16 rows. So in general, there's no reason to believe that there would be a solution to the equation AX equals B for an A matrix of this form. You can think of these rows as rows of data that you're recording on some process, right? And then you want to have a linear estimate, a linear model of the process. That's what we would be generating here. Now, of course, I can solve this. Let's see, I believe with fmincon. So this is an easy problem to solve. I mean, there's a couple ways I could solve this, right? I could solve this by saying, let's say, n equals A transpose A, and then, basically solving A transpose AX equals A transpose B, right? We know that solves this in the closed form sense, and that this has an analytic solution, but I don't want to do that. I want to use CVX to solve it, so let's use CVX to solve it. So up here in my script, I'm going to suppress the output on these so that we don't have to see that anymore. And when I'm scripting, I like to start out just to make sure that I've cleared everything from the previous run. And now we are going to use the CVX command. So we start out CVX begin, and we create a variable. And now we're going to use the CVX command minimize norm a times x minus b and CVX end. The indentation here is not for any purposes other than just good coding practices, right? The indentation is not interpreted at all by MATLAB or by CVX. Okay, so I can run this, and now I get my CVX solution. So we can look at what CVX put out. This n equals 8 is just because I forgot to suppress that. We won't worry about that. Okay, so this is the solver that CVX used to solve the problem. 17 variables, 9 equality constraints. And here we see that 6 iterations. Here is the primal objective value. We also get the dual objective value, and you can see that they're the same in this case, which, you know, strong duality, primal objective equals dual objective. This means we have the optimal solution. Relative gap, essentially 0. You know, these numbers are essentially 0. And then looking down here, the time that it took to solve the problem, the status of the problem. This is important. The status of the problem is that the problem was solved and the optimal value that was achieved, 3.4. So CVX was able to solve this problem as we would expect. For the optimal x, you can see that this x value, this is where CVX stored the optimal x values. So here's my x. So this is the solution to the problem. One thing to note is that this x, my optimal solution, or for example, the optimal value, CVX opt val up here, or any of these values can now be used, you know, in any other MATLAB statements outside of the CVX program. These are global MATLAB variables at this point. Let's look at a situation where it doesn't work. So here, if I were to do maximize and run that, okay, so here I get an error, a disciplined convex programming error. We can't maximize a convex expression. So as we would expected, we'll talk a little bit about disciplined convex programming later on, but for now on, just understand that that's the error that you're going to see if you try to maximize a convex expression or minimize a concave expression. So let's change it back so that it works again. And the first problem that we solved was an unconstrained problem, but we can constrain this problem. So let's change it now to put in some constraints. In order to do that, inside my CVX block of code here, I'm going to keep my variable the same. My variable is x. This is the variable that we're solving for. And I'm still going to minimize the 2 norm, but I'm going to do this subject to some constraints. Let's say 1 is less than or equal to x. Is less than or equal to 5. and we can run that, and now we see we have a new optimal value. The status of the problem is solved, okay, and we can look at the X that we got, and in this case they're all tight on the lower end of the bound. Let's make this a little bit more interesting. Let's set up some random. So I'm going to use the variable L for the lower, and L is going to be min we're going to do this randomly again. So we're going to set up something called bounds, which is just generated randomly, and then we're going to make lower, or L, we're going to make that the min, and we'll make an upper bound. This is all being done outside of the CVX text block. And now we will change this to L and U. And we'll run it again. Okay, and now we see that our X's are in between some lower and upper bounds that were generated randomly in this line 10. In CVX, you'll note that this norm function that we're using defaults to the to norm if it's unspecified, but we can make this any norm that we want. So, for example, I can make it a 3 norm, and we can run it. And if I wanted it to be the infinity norm, I would just put INF here, and that will run as well. So this is a CVX command. There's a list of CVX commands in the documentation. Norm is one that's commonly used. We'll see several more as we move through. Let's look at a couple other features of this program with respect to CVX syntax and things like that. So the first thing that we can look at is this variable here. In CVX, any variable that's being used in either the objective function or in a constraint, so here we used X in the objective function, we used X in the constraint, that was the only variable, but any variable has to be declared if it's being used in a constraint or an objective function. So we do that by using the command variable and then the name of the variable, and we can specify the dimension as well. So in this case, this variable is X. It's a vector of dimension n, where, in this case, n is being set to be 8, right? Because if you think about ax minus b, a we've set up to be 16 by 8, so a times x has to be 8 elements long, a vector of 8 elements, right? So that's the size. If we were using a matrix in the objective function, for example, we would say, maybe if we were using a 10 by 10 matrix, then that we were calling X, I would capitalize it then just for stylistic reasons. It would look like that, right? 10 by 10, so we can declare a matrix that way. We could also, if it was a scalar, we would just declare it like that. So that's how we just, I'm going to set this back so that I don't have an error in the program if we decide to run it again. If the this declaration and all the declarations that I've shown so far are for real everything is assumed to be real. If for some reason things were going to be complex, we would just add the word complex onto the end here, and we could then have complex numbers in our variable. We can do other things as well. So, for example, we can specify constraints on the variable. So, one thing I could do here is I could use non-negative, right? So, let's see what happens if I do that. So here, if we look at what happened, the problem is infeasible. The status of the problem is infeasible. The optimal value is plus infinity. And we can see that I wasn't able to get a solution because of that non-negative constraint that I put on x. Other constraints that we can put on, if it was a matrix, we could say semi-definite, for example. If I wanted to do a mixed integer program, I could use an integer constraint. Let's see what happens if I run this with an integer constraint. I get an error here. The problem here, and this is probably something that you'll run into as well, is that the solver doesn't support the solution to integer problems. So you are constrained by what you can do with this free license by the solvers that you have. You've got 2 solvers in here. Additional solvers you would have to pay for. Okay, and in the documentation you'll see a number of other constraints that we can put on our variables in the declaration. Looking now at the optimization function, or the objective function, we've seen there's a number of we've done this 2 different ways. We've done minimize and maximize, and those are generally the ways that you would do it, right? Your objective function is either going to be a minimization or a maximization, but you can also have a problem where you don't specify an objective function, and that would just be a feasibility problem. It's the objective function is set to 0, and if a feasible solution is found, the optimal value is set to 0, and if one is not found, it's set to infinity. Now we have our constraints. So here we have an example of a constraint. If these are inequality constraints, we can also have equality constraints. So if I wanted an equality constraint, for example, x1 is equal to 1, that's how I would do it, right? The equality constraint uses the double equal sign. This is less than or equal to, greater than or equal to. You would just use the greater than sign there. And that is mostly what you'll do with your constraints. We can use the equality constraint to express membership in a set as well. So, for example, the constraint x equal semi-definite n, this means that x is required to be, I should spell it right, x is required to be an n by n symmetric positive semi-definite matrix. So we can do our constraints that way as well. Another way. So the equal symbol here, the equal symbol, is overloaded in the sense that it can mean must be equal to in the case of an equality constraint, or as we're showing here, it's saying it needs to be a member of some set, in this case the member of n by n semi-definite matrices. Okay, earlier we saw an error that had to do with something called disciplined convex programming. Disciplined convex programming is something that's employed by CVX as a means of ensuring convexity. So the idea is that if you follow the DCP rules, you are guaranteed convexity. Now, the rules are sufficient for convexity. So if you follow the rules, you will have a convex expression, but they're not necessary conditions. And so what this means is that you can violate the DCP rules and still have a convex expression, but CVX will not accept it. So let's take a look at what some of these rules are. This is from the user's guide. So here we have valid constant expression is any MATLAB expression that evaluates to a finite value. An affine expression, a constant, a declared variable, and a call to a function in the atom library with an affine result. I'll show you the atom library. It can be a sum or difference of affine expressions, or it can be the product of an affine expression and a constant. Here, a convex and concave expression. These are ones that I particularly want to focus on. So we can have a constant or an affine expression. Again, a call to the atom library. An affine scalar raised to a constant power, so we can have a scalar raised to a power, a convex scalar quadratic form, and I will hit this link after we go through these. The sum of convex expressions, the difference of a convex expression and a concave expression, the product of a convex expression and a non-negative constant, the product of a concave expression and a non-positive constant, and then the negation of a concave expression. So I have something that's concave, I negate it, I get something that's convex. And then the ones down here are essentially one for one on the ones up here, just for concave rather than convex. Now, if we look at, we'll go over these scalar quadratic forms. So here you see what is and is not allowable in terms of the DCP rules. So interestingly, here we see we can't have quadratic expressions such as this multiplication. So here they say they've chosen to make an exception to the rule set to allow for certain quadratic forms that map directly to convex quadratics, and these are those. Okay, and you'll see additional, you'll see, like, for example, this expression is not allowed. However, this expression, which does the exact same thing, is allowed. So, here the problem is this multiplication, right? This multiplication is problematic in terms of DCP. The correct way to express this in terms of DCP is like this. Okay, there's a number of examples like that. For example, the entropy function, if you type out the entropy function, it doesn't follow the strict DCP rules. However, there is an entropy function in the atom library. I think it's ENTR. A call to that does follow the DCP rules. Okay, so that's a basic introduction to CVX and to the principles behind DCP. We'll come back on the next video with some more sophisticated examples from the text.